Assalamualaikum. I am Amal Insyirah binti Sa'ari, and today I am honored to present my thesis on the characterization of layer double hydroxide rice husk biochar composite in synthetic wastewater treatment. Here is an outline of my today's presentation. My presentation consists of introduction, literature review, methodology, result and analysis, lastly conclusion and recommendation. Our study aims to address the critical issue of heavy metal contamination in water and explore advanced treatment methods using innovative composite materials. Let's start by understanding the context and significance of this study. Industrial activities release a variety of pollutants, including heavy metals, into water bodies, which may pose to the significant threats to the environment and human health. Traditional wastewater treatment methods often fall short in effectively removing these pollutants, necessitating the development of advanced technologies. Layered double hydroxide, which is LDH, are promising materials due to their unique layered structure and ion exchange properties, while biochar derived from agricultural waste like rice husk, which will enhance the absorption capacity due to its high surface area and porosity. Next, we move to the problem statements of this study. The discharge of pollutants, especially heavy metals, into water bodies is predominantly attributed to industrialization, which the industries such as battery manufacturing, electroplating, mining, and refining will release heavy metals like cadmium, lead, mercury, copper, nickel, chromium, and arsenic into the environment. These metals are highly toxic and pose to a severe health risk even at low concentrations. For instance, lead and copper, widely used in industries, can cause serious health issues including organ damage and cancer. The presence of these metals in water necessitates the developments of technologies capable of efficiently removing them to prevent adverse environmental and public health impacts. This research tackles important issues in cleaning wastewater and protecting the environment. The main focus is on removing the lead and copper ions by using a new material made from zinc, magnesium, aluminium, LDH, and rice husk biochar. This is important for several reasons. Firstly, effectively removing these heavy metals from wastewater will help to reduce the pollution and protect our water resources. This is crucial for keeping ecosystems healthy and ensure that we have a clean water for various needs. Second, by getting rid of heavy metals from wastewater will decrease the risk of people being exposed to harmful substances, which protect public health. Lead and copper, which can cause serious health problems, include organ damage and neurological issues. So by removing them is important for our well-being. Third, by using rice husk biochar in the composite material, will provide a sustainable way to dispose of agricultural waste. This not only improves the material's ability to absorb pollutants, but also promote recycling of agricultural waste, contribute to better waste management. Additionally, this study helps in developing more effective materials for removing heavy metals, which advanced technology used in wastewater treatment. The innovative composite material created in this research shows great promise for practical use in water treatment. Finally, the research offers the valuable insight into how zinc, magnesium, aluminium, and rice husk biochar composites are made, their structure, and their chemical properties. This knowledge is very important for future research and innovations in environmental cleanup, leading to more effective and sustainable solutions to water pollutions. Here are the main objectives that guided our research. The objective of this study are to investigate the removal mechanism for lead and copper ions. Secondly, to develop a novel composite material by using co-precipitation and hydrothermal techniques, and to analyze the morphology and functional group on the composite surface. Next, we move to the literature review section. Layered double hydroxide are characterized by their brucite-like layers and are extensively used in catalysis and anion exchange processes. LDH, which consists of cationic metal layers with hydrated anions in the interlayer spaces. These materials can intercalate a diverse array of anions making them highly versatile for environmental applications. The general formula, as you can see in the slide, where M2 plus and M3 plus denote divalent and trivalent cations respectively. And next, we look at the synthesis technique of zinc, magnesium, aluminium layer double hydroxide, which has been explored by using various techniques. Same image have shown the surface characteristics, while some EDX analysis confirm the distribution of elements. Incorporating LDH into rice husk biochar will enhance their adsorption capabilities as seen in SEM and FTIR analysis. This technique will help us understand the structure and functionality of the composite, which is crucial for their application in wastewater treatment. And different methods are used to synthesize LDH biochar composites, including hydrothermal synthesis and co-precipitation. Now, let us move on the methodology that have been employed to achieve this objective. This methodology was divided into three sections. Firstly, the preparation of LDH composites. Secondly, the preparation of synthetic wastewater. And lastly, batch testing and analysis. We go to the first section, which is the preparation of zinc, magnesium, aluminium, LDH composites. The composite was prepared by mixing zinc, magnesium, and aluminium nitrates with rice husk biochar, and the mixture was subjected to hydrothermal treatment at 180 degrees Celsius for 24 hours. And next, we move to the preparation of synthetic wastewater. The synthetic wastewater containing 400 ppm of copper and lead ions that was prepared for the test of the composite effectiveness. And next, for the batch testing, involve adjusting the pH of the samples and analyzing the result by using the ICP-OES, SEM-EDEX, and FTIR. This is removal efficiency calculation of the heavy metals of copper and lead. This formula were used after we analyze the sample by using ICP-OES. Now, we will discuss the removal efficiency of copper ion and lead ions by using our synthesized zinc, magnesium, aluminium, LDH with rice husk biochar composite. This study focused on the individual absorption behaviors of these ions from synthetic wastewater samples, namely copper SW and lead SW. Let us begin with the calibration of ICP-OES for copper and lead. Calibration curve ensure our measurements are accurate, and here we see the mean corrected intensity for standard solution of copper and lead. The correlation coefficient for copper and lead were 0.9956 and 0.9957 respectively, which indicate the excellent linearity and reliability. Next, we examine how pH affects the removal efficiency of copper and lead. This graph illustrates removal efficiency across different pH level for 4 samples. Optimal pH level are critical for maximizing removal efficiency. For removal efficiency of copper in copper SW sample were 96.95% at pH 3 and 99.72% at pH 7 and 99.95% at pH 10. For lead in copper SW sample, the efficiencies were 99.52% at pH 3 and 99.99% at pH 7, and lastly, the same percentage, which 99.99% at pH 10. In leads SW samples, the copper removal was 99.79% at pH 3 and 99.99% at pH 7, and also the pH 10 recorded the same percentage at 99.99%, while lead removal was 93.04% at pH 3, 99.89% at pH 7, and 99.95% at pH 10. pH is a critical factor that influences the absorption efficiency of heavy metals. It affects the surface charge of the absorbent, the degree of ionization of the absorbate, and the extent of metal ion speciation in the solution. Now, let us look at the FTIR analysis of the LDH and LDH with rice husk biochar composite. In the zinc, magnesium, aluminium LDH composite, we observe key functional groups such as hydroxyl at 3495.8 and the carbonyl at 1638.1 and the metal oxygen bonds at 556.4. These groups are crucial for the absorption process. And for the LDH with rice-husk biochar composite, similar functional groups were present with slight shift in with numbers. The hydroxyl group was observed at 3,465.6 and the carbonyl group at 1,640. The presence of silicate group at 1,013.8 from biochar indicates enhanced surface area and porosity, which are beneficial for absorption. Next, let's examine the FTIR spectra of the copper SW sample. For the copper SW sample, the FTIR spectra show consistent hydroxyl stretching peaks around 3,838.80 and the carbonyl groups at 1,616.87 across all pH levels. At pH 10, the additional peaks for alkyne groups at 2002.03 and alkane stretching at 2,865.38 were observed. This indicates that functional groups on the composite interacted with copper ions, which enhancing the absorption process. Okay, let us review the FTIR spectra of lead SW samples. For lead SW sample, the hydroxyl stretching peaks were observed at 3,836.46 and carbonyl groups at 1,614.24. At pH 7, the additional hydroxyl peaks around 3,712.12 were seen in the spectra. At pH 10, the silicate groups were noted at 1,009.97 and there was an additional peak for alkyne groups at 2,000.33. This shift suggests that the effective interaction between lead ion and the composite material itself. This is the comparison of the FTIR spectra of the composite for the before and after absorption. This slide shows the spectra for zinc, magnesium, aluminium, LDH and LDH with rice-husk biochar composite, as well as the sample after absorbing copper and lead ions at pH 10. The consistent of hydroxyl stretching peaks and the shift in carbonyl and metal oxygen stretching peaks confirm the successful absorption of metal ion. This shift illustrates the formation of coordination bonds and highlight the enhanced absorption capacity of the composites. Next, let us first look at the SEM EDX analysis for the LDH composite. SEM image show a flake-like morphology which indicate a high surface area that beneficial for absorption. EDX analysis confirm the presence of essential elements with the following composition such as carbon 32.33%, oxygen 34.47%, magnesium 8.23%, aluminium 2.19% and zinc 22.88%. These structural features contribute to the composite's effectiveness in absorbing the heavy metals. Next, we examine the LDH with rice-husk biochar composite. Same image reveal the fine crystalline LDH particles distributed across the rough surface of the rice-husk biochar. EDX analysis show the successful integration of LDH onto the rice-husk biochar with the following composition such as carbon 9.52%, oxygen 42.78%, silicon 0.10%, magnesium 15.93%, aluminium 6.09%, and zinc 25.57%. The rough surface and distributed particles indicate a strong interaction between LDH and rice-husk biochar, which enhance the composite absorption properties. Now, let us review the SEM EDX results after the composite absorbed copper ions in copper SW samples. The SEM image displayed a more granular and less porous surface morphology with visible aggregation of fine particles. EDX analysis confirmed the presence of copper and with the following elemental compositions such as carbon, oxygen, silicon, magnesium, aluminium, and also the percentage of copper is 4.24%. And these changes suggest successful absorption of copper ions with the formation of aggregation, which indicate the effective incorporation within the composition. Lastly, we examine the composite after absorbing lead ions in lead SW samples. The same image shows significant morphological changes with more defined and deeper cavities and pores formed on the surface of the LDH and with rice-husk biochar. The EDX analysis confirmed the presence of lead with the following composition percentage, which is 14.52%, and the structural reorganization and high lead content indicate the successful absorption of lead ions, which enhance the composite functionality for heavy metal removal. Now, let us move on the key findings from this study on the characterization of the LDH with rice-husk biochar composite in synthetic wastewater. First, this composite material showed the exceptional removal efficiency for heavy metals. Specifically, this was observed that copper removal reached up to 99.95% at pH 10. For lead ion, the removal efficiency was as high as 99.99% at both pH 7 and pH 10. These results highlight the composite's effectiveness in absorbing these ions. Next, I found that the highest absorption efficiency were achieved under neutral to slightly alkaline conditions. The effective deprotonation of functional groups at higher pH levels facilitated better absorption. This means that the composite works best in environment with pH level around 7 to 10. This FDIR analysis provides significant insight into the chemical interaction which involved in the absorption process. I identify the key functional groups such as hydroxyl, carbonyl, and metal-oxygen bonds. This group play the crucial roles in the absorption process. The interaction between this functional group and the metal ions was confirmed, which enhanced the composite absorption capacity. Through SEM EDX analysis, I observed a flake-like morphology and fine crystalline particles on the surface of the composite. This indicates a high surface area which is beneficial for absorption. EDX analysis further confirmed the presence of essential elements like carbon, oxygen, magnesium, aluminium, and zinc, which show the successful formation and integration of the composite material. I also examined the composite structure and functionality post-absorption. The composite maintained its structural integrity after absorbing lead ions and copper ions, and significant morphological changes observed in SEM image indicate that the successful absorption with more defined and deeper cavities forming on the composite surface. I identified the primary mechanism for metal ion removal, which include ion exchange, surface complexation, and electrostatic attraction. The composite material provide multiple active sites and a high surface area which contribute to its efficient absorption performance. Lastly, these findings suggest that the zinc magnesium aluminium LDH with rice-husk biochar composite hold the great potential for real-world wastewater treatment application. To further validate this potential, future studies should focus on pilot-scale testing, assessing long-term stability, and evaluating the economic feasibility of the composite. To conclude, this study successfully developed a novel composite material combining zinc, magnesium, aluminium, LDH, and rice-husk biochar for the effective removal of heavy metals from synthetic wastewater. Our results demonstrate that this composite material is highly efficient in absorbing lead and copper ions, significantly reducing their concentration in water. The combination of LDH, ion exchange properties, and biochar, high surface area, creates a synergistic effect that enhance the overall absorption capacity. We found that the composite material achieved high removal efficiencies with up to 99% for lead and 97% for copper under optimal conditions. The detailed characterization show the successful integration of LDH and biochar, and the composite consistently performed well across various pH levels. This indicates that the developed composite material is a sustainable and effective solution for treating heavy metal contaminated wastewater. In terms of recommendations, further research is needed to scale up the synthesis process and test the composite in real-world wastewater samples to validate its practical applicability. Material optimization should also be explored, including different ratios of LDH to biochar and investigating other types of biochar to enhance the material absorption capacity. Additionally, implementing pilot project to evaluate the performance of this composite material in industrial settings will provide the valuable insight for large-scale application. Conducting a comprehensive environmental impact assessment will ensure that the production and use of this composite material are environmentally sustainable. Our study offers a promising approach to mitigating heavy metal pollution in wastewater, which will contribute to environmental protection and public health. Thank you for your attention, and I am happy to answer any question you may have.